So in our last class, we already mentioned that a system is an abstraction of anything that takes in an input, then operates on it, then produces an output, such that the output itself, say Y in this case, is seen to be a mapping of K and X, where K here is the mapping function. Okay? So this describes the properties that characterizes this system used to transform X to Y. So for instance, we want to have Y to be a function of X, then there is this metric, okay, which describes the property of the system. It tells us the type of system we are dealing with. And in the last class, we made mention of continuous time systems, discrete time systems. Then we went on to talk about static systems, such that given an input to a system, the output is a function of the input at that instant of time. Okay, and then we now said when the system's output is dependent on the present input and some other parameters relative to some other time instance, either in the past or in the future, then we have a dynamic system. Okay? And then we also made mention of the causal system. Okay, because what we are going to be dealing with are literally going to be linear time invariant systems that are causal LTI systems. And these systems are systems, you know, that depend only on the present or past values of the input. So they have nothing to do with the future values of input, okay? So causal systems are systems that are not dependent on future input. While the non-causal systems are systems that are not causal. So these are systems whose output at the present instant of time may depend on the past, present, and future values of the input. We also made mention of anti-causal systems, which are systems whose output at the present instant of time depends only on the future values of the input. Okay, and we said that all non-causal systems are not anti-causal because anti-causal systems depend only on the future values of input, while we have some other systems that may depend on both the present input and future inputs. Then we didn't stop there. We made mention of linear and nonlinear systems, and we said that linear systems are systems that obey the principles of superposition. In other words, they obey the law of additivity. So let's assume we have a system such that S1 of t is fed into the system, and then we have Y1 of t. Then if, for instance, we have another input to the system such that we have Y2 of t, for instance, then should we add up this input x1 of t plus y plus, s2 of t fed into the same system, then the resultant effect should give us y1 of t plus y2 of t. This is the principle or the law of additivity. And we said that for a system to be linear, it has to obey both the law of additivity and the law of homogeneity. And we said that the law of homogeneity has to do with scaling, okay? So in other words, should we scale the input, say s of t, by some parameter k, and feed that into a system, then we should get y of t to be the scaled version of s of t, okay? Now, the same thing applies if, for instance, we pass the signal into the system and then have our output such that we now scale this output by that same parameter, then we should have y of t to be the same as s of t. Okay? So for such systems that obey the law of additivity and the law of homogeneity, which is scaling, then we say they are linear systems. But systems that don't obey these parameters, meaning they do not obey the principles of superposition, we say they are non-linear systems. And in practice, most of the systems we get to deal with in real life are non-linear systems. And interestingly, you must have been taught circuits, linear circuit elements, the lump parameters, and all of that. Well, you were made to understand that these are linear systems. But soon you realize that they are only linear based on certain conditions. And should those conditions be violated, they become nonlinear, okay, including your resistor, your capacitor, and the likes. Okay, so in other words, given a particular operating condition, they could be linear. Let's assume your resistor, which we are going to mention shortly when in terms of modeling of LTI system. We understand that there's a linear relationship between the current and the voltage given your resistor, such that the resistance bears this linear relationship. But should the voltage value exceed the threshold for which this linear relationship holds, then this resistive element could burn out. So at that instant where it burns out, then it means the principle of linearity is violated. And as such, the system begins to behave in a non-linear approach or manner. The same thing goes for capacitors, inductors, and that. So long these long parameter elements are operated within the operating conditions or designed operation condition, then where we could adjudge them to be linear elements. But in practice, what I would love you to understand is that most systems are nonlinear. But for ease of analysis, we want to assume, more like a reference point, to make our analysis a little easier. Then we also talked about stable systems. We say Bible. So bounded input, bounded output. So, and there we made mention of, so such systems are called stable systems, okay? And when we say bounded input, it means that the amplitude is finite, okay? Finite amplitude, and finite amplitude. So the input, so it means that the input has finite amplitude and the output also has finite amplitude. And some examples of signals that have, not signals, not all, well, of signals that we could say have finite amplitude. We have your unit step function, we have your sine wave, we have your cosinusoidal waves, and all of that. So they have bounded input values because their amplitude parameters are finite, okay? The amplitude, say A, is finite. Unlike your ramp function, which has an infinite amplitude, okay? So should we feed a system with a signal, with a bounded input signal, and then have a bounded output signal, meaning the output signal after being operated on by the system is also of finite value? We say such a system is stable. Now, what if we feed a system with a bounded input signal and then the output is unbounded, like we checked out in our last class, where we fed the system your unit step function, we fed it into a system we could otherwise refer to as an integrator. Then we got a ramp. So such a system is not stable, it's unstable, okay? Well, that's fine. So today we are going to go into linear time invariant systems. And this is what we are going to be talking about for the rest of the semester, for the remaining part of the semester. Okay, we have quite a number of guys in class now. So let us jump right in. Oh, okay. So LTIs. So like we already explained, we said these systems are both linear and they are time invariant. So they are time invariant in that given a system and such that the system is fed with an input, say S of t at a particular instant of time, whatsoever we get as the output, should we feed that input at some other instant of time, we should get that same output. That's what it means by time invariant. So the response of the system to that signal does not change with respect to time. And then for it to be linear, then it means that it obeys the principle of superposition. So it means that the law of additivity and the law of homogeneity applies. So here you should note that the continuous time system, because we have discrete time systems and continuous time systems. I'm going to be putting them all together, but we'll emphasize the continuous time systems. So understanding the discrete time system won't be a problem. Now, the continuous time systems are described by differential equations, and usually they have the general solution such that it is the sum of the zero state response and the zero input response, okay? And before I go on, I would like to pull our, let's go back memory lane. let's put it that way. Now, when you solve your differential equations, you come up with two solutions, the particular and the homogeneous solution. Well, we'll still come to that as we talk about all of this. Now, so long we are able to describe the continuous time system using differential equations, as we'll see shortly, then the general solution, which consists of particular and homogeneous solution, applies. And now that we have to deal with LTI systems, we still have two parts to the solution, okay? So the solution of an LTI, meaning a linear time invariant system, consists of two major components, right? First is the zero state response, which we call Z as R. And then the second is the zero input response, which is ZIR. So the zero state response is also called forced response, while the zero input response is also called natural response. Okay. So since the linear system produces an output whose value is dependent on the present input, so it means that if we feed the system with, say, X1, we are going to get Y1. So say X1 is fed into the system, then for it to be linear, we're going to get Y1. Let's say S1 of t, Y1 of t. So at some time instant of 0, then it means that we are going to get Y1 of 0, right? Meaning the linear system should produce an output of 0 if the input is 0. Okay, that's what it means for the system to be linear. So in analyzing the LTI system, then we can now separate the solution into these two folds. And the zero input response, therefore, is the output of the system when the input is set to 0. Okay? This is, let's change the color. Output of the system when the input set to 0. to 0. So we can say this is the response to the initial conditions only, right? Response to the initial conditions only, right? While for the zero state response, which is also called the force response, from the word force, it means that we have to apply something to it, right? So it means that the output is when an input is applied, okay? So it is the output of the system when an input is applied. The output of a system when an input is applied. So that the complete solution, therefore, of an LTI system, the complete solution of an LTI system will therefore be given as total solution be the same as zero input response plus zero state response. Is this clear? Before I go on and on and on.
Yes, sir.
Okay. If that is clear, then I'll just move on then. Okay. Now, if this is clear, so it means that if the zero state response is the same as the force response, so if the initial state is 0, then the system is initially relaxed, right? Because nothing is happening. So that's the initial state. Probably the switch is turned off. Okay, so nothing is happening. So we have a system, a lighting system, for instance, and the switch is turned off. So that's the initial state is 0. So, and then the excited output, right? Excited, see here, excited output is a force response, right? So if I should hit that switch, then light comes on. So we can therefore say that the zero state response, or better still, the force response, is the same as the output y of t for all parameters of t greater or equal to 0. That's for time instance other than 0, other than the initial state, excited by the initial state S of 0 being 0, for which this is initially relaxed. And then S of t, which is not the same as 0, is some value. This is for some time t greater or equal to 0. So this is the implication for a zero state response. So it means that we have to move off the initial condition and then get to some value where the system is excited. Now, for the zero input response, or better still, the natural response, this implies that the input is identically 0 for all values of t. for all values of t greater or equal to 0. So in other words, a zero input response means the natural response. Okay, nothing is happening. So we can now say that the zero input response or the natural response is the same as the output y of t for all values of t greater or equal to 0, which is excited by s of t being some value other than 0 for some t less than 0. And then it is going to be the same as 0 for all values of t greater or equal to 0. Okay? So recall that for the zero state response, the value of s of t is not 0 for values of t greater or equal to 0. But for the natural response, the value of s of t is the same as 0 for all values of t greater than 0. So meaning at some time instance other than 0, the value is 0. So it's the input value is identically 0. So now this brings us to the point of saying that the zero state response y of t for t greater or equal to 0 excited exclusively by the input s of t for t greater or equal to 0, and then for zero input response y of t for t greater or equal to 0 excited exclusively by the input s of t for t less than 0. Now, we can also conclude that for the zero input response, we require the input to be identically 0 for all values of t greater or equal to 0, like we mentioned here. And also, for the zero state response, we also require that the input be identically 0 for, okay, I didn't use the symbol already, so let's just, for all values of t less than 0. And now, this implies that we could replace this by a set of initial conditions, which is the initial state. Now, if that is clear, we can now go on to the modeling of LTI systems. But before I go into the modeling, I think I would love to mention something here, okay, before I go into the modeling. Now, as we have discussed so far, because we need to know the nature of the signal we are actually dealing with, okay? We've already mentioned that for us to analyze, or better still, solve that problem posed by a linear time invariant system, we have two parts to it, just like we have two parts to solving a differential equations, where we have the particular and, you know, the homogeneous equation. But now we have the zero input and the zero state response part to it. But there's a way the signal itself we have to deal with behaves. Okay? Okay. Now, if, excuse me, now, if the input and output are functions of time, like we mentioned earlier, we have S of t gets into a system, and then we're expected to get y of t. So it means that the input and the output are functions of time. Okay? But in practice, systems are easier to analyze when the input and output are functions of frequency. Why is that? Why is that? Why can't we just analyze the systems in practice in the time domain? Why in the frequency domain? We mentioned that in our first class. That's the reason for switching techniques. We will have the transforms, right? But why? So let's look at a typical signal. So we want to formulate a typical signal. We already established in our LS lectures that a signal in practice is a combination of an even and an odd component. So let us take a typical signal, S of t. You see that we have the even component, and then we also have the odd component. Okay? And if that is what it is, we can also represent this in the Euler form, which is the same as epsilon jt, which is the Euler form. And now you will see that this signal is represented as a complex quantity. So it means that S of t is a complex signal that comprises of the real part, which could be sigma, and the imaginary part, which we could say is the same as j omega. So if we plot the real versus the imaginary part, then what we get is an x-plane, okay? The real versus the imaginary part. So this gives us an x-plane, for which S is the same as sigma plus j omega. We already know that omega is the same as 2 pi f, for which f is the frequency component of the signal. And you will also observe that this frequency component is contained in the imaginary part. It's contained in the imaginary part of the complex x-plane. So if that is what it is, then S of t in relation to the x-plane can be designated as S of t being the same as epsilon st. So we can therefore conclude that epsilon st is the same as the input signal. So for a continuous time system, the function having this type, S of t, is usually referred to as the eigenfunction. Okay? So it means given an LTI system, let's say a continuous time LTI system characterized by some parameter h of s, the eigenfunction, which is the input to the continuous time linear time invariant system, is the same as the scaled version of the eigenfunction, where h of s in this case is also a complex quantity. Is this clear? I'd love to get your feedback. Is this clear?
Yes, sir. We're getting it, sir.
No, sir. Yes, sir.
No,
okay.
sir. Okay. Okay. Yes, that's fine. That's fine. The person that said no, please tell me where you don't get so that I could explain again. What is it you don't understand right now? Hello? I got a no, so I'd love to get your feedback. So I quickly run through that aspect. Okay, there are some messages in the chat room. The relationship with the S-plane, the eigenfunction. Okay, that's perfect. Okay, perfect. Now, if you recall, we made mention of we talked about signals. We mentioned different types of signals, even signals, odd signals, how to manipulate those signals, power signals, energy signals, and all of that. And if you recall, if you were in our first class, which was a physical class, we had a series of physical lectures. You will recall that we made mention of one important point, that signals in practice are complex quantities because they combine the even and odd components. Now, this is an even component, and this is an odd component. And we already know that this is a complex signal. Now, if we should plot this on a scale, okay, recall your complex numbers. We have the real part, real, and we have the imaginary part, right? For imaginary, I don't know, this imaginary, okay. Part. Now, the imaginary part always goes with some parameter J. In our case, we don't want to use I because I is very important to us in electrical engineering. That is correct, okay? So I want to use J, okay? Now, in observing this, we want to say, okay, fine. This component, this complex quantity, which describes the signal S of t, we have always referred to, being a complex quantity consisting of an even and an odd component, can also be written in a compact form, which is the Euler form, okay? Euler form. You know, you have the rectangular form, the Euler form, and all of that. Polar form in complex numbers. You already played with complex numbers. Now we want to apply your complex numbers, which you played with in engineering mathematics, in practical systems. Okay, we need to model a system we could synthesize, for instance, or we could design, or we could implement. Okay, now, if this signal S of t is a combination of the even and odd component, then it means that we can actually plot this on a complex plane where we are able to separate the imaginary and the real component. Don't forget that cos t plus j sine t is the same as epsilon jt. It's the same thing. This is just the Euler form, right? If that is clear, now, if we want to plot this in the complex plane, then we'll have to separate the real part and the imaginary part. That brings us to the S-plane. This is the S-plane, where the S-plane is also the sum of the real and the imaginary, right? This is the real part, and this is the imaginary part. So if we try to replace our signal by plotting on the x-plane, so it means that we are going to have the sigma being the real component on the real time, on the real axis, while on the imaginary axis, we are going to have the j omega. We already know that the j omega is the same as 2 pi f in your basic science. Because this now is going to also arm us with enough information why we prefer Fourier analysis for practical systems and not Laplace transform. Okay? Largely because of this imaginary component. We are interested in the frequency component of the signal. And recall I already mentioned that in practice, it is easier to deal with systems in the frequency domain. Okay? In the frequency domain and not in the time domain. Okay? Now, this is my time domain, right? And I already represented this signal in this format. But now that I have moved from this format to the S-plane, so I don't want to replace my signal anymore with cos t plus j sine t, and I want to replace my signal with the real and imaginary component. And should I try to represent my signal, my complex signal in this form, in terms of the X domain or X plane, then I'm going to have this rather than this. Okay, it's more like coming from axioms now. You know, we just want to pull through from, you know, a particular notation and say, well, James, for instance, is a boy. Okay, and then we also know that Tom, for instance, is also a boy. So we can now tell that they have equivalent anatomy, right? That's more like this. Now, James is a boy is an axiom. We may not be able to prove it, but we just assume so based on some inferences, right? Tom too is a boy. So if both of them are boys, they may not look alike, but no doubt their anatomy will be similar. The same for a girl, okay? Based on their anatomy. That's what we're trying to say. Well, the signal S of t is of this form. And we know that expressing our signal in the Euler form is a combination of the even and odd component, which means that it has a real part and it has an imaginary part. Also, in the X domain, in the X plane, we have a combination of the real and imaginary part. And we know in that dimension, the imaginary part contains the frequency component, where omega is the same as 2 pi f. Okay? Now, if that's what it is, we can now write our signal to contain the component as we have in the S domain, in the S plane. So rather than say S of t is the same as ejt, then we can say that S of t is the same as est, for which S describes the component of this signal in the X plane. And from this, we can say that this is the same as epsilon sigma plus j omega t, which is the same as epsilon sigma t, epsilon j omega t. So, well, when we begin to analyze transforms, you will now see how we play with this. And what we now want to say is that this parameter we just explained or we just showed here is the eigenfunction, which is the input to a continuous time, linear time invariant system. Hello?
Hi, sir.
Hi, sir.
Is it making any sense for now?
It's making sense.
Yes, sir.
Okay. So as we go on, you are going to be hearing eigenfunction, eigenfunction. So once I mention eigenfunction, just know this is the input to a continuous time, linear time invariant system. Probably I don't want to say S of t anymore. Okay. So once I mention eigenfunction, just recall that we are talking epsilon st, est. Okay. Okay.
Okay, sir.
Yeah. Now, if you agree with that,
Excuse me, sir.
yeah,
Excuse me,
go
sir.
ahead.
Before you proceed, sir. So, you said something that it's easier to treat our signal in the frequency domain. So, in case we are being asked that why, why is it easier for us to treat our signal in the frequency domain? What will be the answer, sir?
Okay, why? There are quite a number of interesting reasons. And as we get into full transforms, you will understand even way better. But let's start from one point. Now, if I have to transmit a particular signal, okay, for telecommunication purposes, for instance, telecom or telecom, let's put it as telecom, for instance. Say I want to transmit a signal, okay, telecom. What will come to mind? What do you think? Okay, fine. You are using your mobile device, right? We know you've moved from GSM to high-speed packet access to LTE, now to 5G, and now we're heading to 6G. What's the difference between all of these technologies? Why are we moving from 2G, 3G? Can you bear any, is there anything that comes to mind? You know, when we begin to talk, what comes to mind?
Speed, sir.
Yeah, what?
Efficiency.
What's that? Yeah,
Speed.
speed, right? And one thing that is different is the frequency of operation, right? At some point, we're using 900 megahertz. We say that is GSM, 2G. Then we also moved to 1800 megahertz. Well, we optimized for capacity. We went to 2100 megahertz. Then we said this is 3G, on and on. And now we're trying to use even lower frequency bands, 800, as a mix of all of them for 5G, 6G, and all of that. Now, these frequencies you are talking about, they are mapped into channels, okay? Now, when you begin to talk about your bandwidth, we are talking in terms of frequency, okay? We're talking in terms of frequency, okay? So at the end of the day, you want to analyze a particular signal. You get a spectrum, right? Okay, what do? You're analyzing the frequency components of that signal, isn't it? Hello?
Yes, sir. Yes,
Yeah.
sir.
Yes, sir. Yes, sir. Yes, sir.
So everything we get to do, you want,
Yes, sir.
yeah, want to operate at some frequency domain. Okay, fine. You want to filter noise, probably your radio system. You want to design a tuning circuit, and you want to design a filter that's going to cut off certain what? Frequencies, isn't it? So you now see that everything we get to interact with going forward in terms of designing practical systems, we have to deal with frequency components. Okay, it's either we want to filter those components, we want to use a particular frequency, frequency band in the spectrum or whatever, and that's fine. And then the analysis, also the mathematical rigor we go through in the time domain is quite tedious. Okay, just imagine we'll come to convolution soon. We want to start dealing with some integrals in the time domain. Now, in the time domain, we are doing convolution, but in the frequency domain, we are doing multiplication. It's easier to just multiply, right? Yeah, so in the frequency domain, analysis is made easier. So there are a lot of factors to consider, okay, coming from what we want to do, what we have to deal with, and the ease of analysis. But for me, I would say, well, for ease of analysis, in the time domain, I begin to do convolution and all of that. I rather just move to frequency domain where I just multiply those components or those values. Okay?
Okay, sir. Thank you, sir.
Yeah, so there are so many, you know.
Thank you, sir.
There are so many, what's it called now? Properties or benefits or whatsoever we may figure out as we progress. Okay? Okay.
Okay.
Okay, so now we have this. So I think this board is looking messy. So let's clear it and so we could get a clear head. Now, we already mentioned now that EST is the Eigen function, which is the input to a continuous time linear time invariant system characterized by some parameter h of x, such that our output is the scaled version of the Eigen function. And I already mentioned that this scaling parameter or coefficient is also a complex number. It's also a complex number, okay? And the value of this complex number depends on the frequency S, okay? The value depends on the frequency S of the input signal, right? Okay. Now, if you multiply a signal by a complex number, what will you get? What happens? What happens? So let's assume I have a signal, say, 2 theta or 2. Let's position this properly. So let's assume we have a signal 230°, and then we have another signal 445°. You know, this is polar, right? We could represent this again in the Euler form, right? So this is a complex now signal, isn't it? You recall your complex numbers, right?
Yes, sir.
So we could put it this way. So what format is this?
Polar notation, sir.
Polar notation, perfect. So it could be in Euler, it could be polar. So I just put up my complex signal in this format. So if I should multiply these signals, what will happen?
It changed the direction, the plane, sir.
It will change the plane. What will happen to, meaning the magnitude and the phase, right? Something will happen to the magnitude, and something will also happen to the phase, right?
Yes, sir.
Because the angle will change. So when we multiply this, what will happen to the angles? Are we adding or subtracting the angles?
We are adding the angle, sir.
So we add the angles and we multiply this value. So it means that should we multiply a signal by a complex number, it means that there will be a change in the magnitude and phase. That's what it means, right? So this particular parameter is a complex number. So once we pass this eigenfunction through a system whose properties is characterized by a complex number, so it means that technically the magnitude and phase of the signal will be altered, right? Will be altered. And now, if the magnitude and phase is altered, you can now see why it gives us, we enjoy playing in the frequency domain. So in terms of analyzing all of these magnitude phase difference in the frequency domain, we just do some multiplication and addition of some angles and all of that, right? Which in the time domain, we'll have to go through some rigorous mathematical activities. So, like I already mentioned in the lecture, in the video, in the lecture series, you will also observe that for us to really say that this is an eigenfunction, you see that all the frequency components of this particular input parameter is also present in the output. Okay? Now, what if, for instance, we multiply this signal by a unit step function? And you know that a unit step function is going to clip this signal at some value of t less than 0. So it means that all the frequency components contained in this eigenfunction at some value less than 0 will not be present at the output. So it means that ESTU of t is not an eigenfunction. Because for EST to be an eigenfunction, it means that the frequency components in the input must be present at the output. Is that clear?
It's getting clear, sir.
Yes, sir.
Thank you, sir.
Yes, sir.
Okay, now if you just, let's assume you didn't lie to me by saying it is clear, then let us go into the modeling, okay? The modeling of these systems, okay? So one model now, modeling of LTI systems. I'm sure this is not in the video, okay? So we just update. Okay. Modeling of LTI systems. Okay. Now I mentioned just in passing that your linear elements, like we have, let's say linear elements, right? Like we have your resistor, for instance. You already know that the voltage applied across this element has a linear relationship with the current, I of t, okay? And this exists, this linearity property exists within the power limitations. Okay? So in other words, within power limitations, the resistor is a linear element. Okay. Now what happens if we exceed the power limitations? What will happen?
It burns out.
It burns out. So when it burns out, what happens? Will it still be a linear element?
No, sir.
No.
It's not linear.
No, sir. No, sir. It will
So
not
it
be
will
linear element,
cease,
sir.
yeah, it will cease to be a linear element. So in practice, a resistor with resistance R is not linear, because if the applied voltage is very large, then it will burn out. Then it will be linear. But theoretically, we try to say, well, it is linear for ease of analysis, right? So were you lied to all these years? I don't think so. But you were not told the whole truth, okay? So now, another interesting element is your capacitor. We know that the charge has a linear relationship with the voltage, such that the current is the same as C dV of t dt. So if we disregard saturation, for instance, the charge stored in the capacitor is related to the applied voltage by a linear relationship here. But what if we consider saturation? What will happen? The capacitor will cease to be linear, okay? Because at some point, the value will saturate. It won't just go linear, then we have some saturated value. The same for inductors. Okay? Now we have the flux to be related, linearly related to the current, such that the voltage value is the same as LDI of t dt. So the flux generated by an inductor is related to its current by a linear relationship. But in practice, well, the inverse is true. But you will observe in this relationship that we are gradually coming to some differential notations. And we use differential notations. So you will observe that these elements interpretation relative to the time scale results in differential equation. And that brings us to modeling, the modeling of the systems, okay? So first of all, you will know that a system is anything that establishes a relationship with its input and output. We already said that, okay? So it means that we have a system. So it is only a system. It is a system because there is a relationship between the input and the output. Else, it will not be a system. So, and one way to model continuous time systems is through differential equations. Yeah. We use differential equations, and you've done that in your engineering mathematics. So we're going to apply it this time, okay, in terms of modeling systems. And you know that the complete solution to a differential equation, just like I mentioned earlier, we're not talking about LTI systems now. We're talking about continuous time systems, or better still, just differential equations. You were told, in fact, you actually passed that course. That's why you are taking this course. We have the particular solution. And then we have the homogeneous solution. So these two put together gives us the total solution of a differential equation. And we already know, let's change this color. We already know that the particular solution is one for which the function or satisfies the differential equations, okay? Particular solution is one. Is any function that satisfies the differential equation. While for the homogeneous solution, the solution of the differential equation with all inputs set to 0. Okay? Now, we don't want to go into this because you already resolved all of this in your engineering mathematics, okay? In your engineering mathematics, okay? So we just applied in this time. So we already know once we are able to analyze our system to the point that we are able to represent these components using differential equations, you already saw that here. So the relationship between current and voltage brings us to those differential parameters when we begin to use storage elements, okay? And with those, we could model practical systems, okay? Now, what I want you to understand is this. If we are able to do this, if we are able to represent our system using differential equations, then we could model the system by, either by using a graphical approach, or better still, using the state space approach. We'll just consider those two, okay? As an addition to whatever we may have done in previous lectures. Okay, so let us consider the graphical representation or modeling. Let's say graphical modeling of continuous time systems. Okay. Now, here, this approach, we'll call it the integrator, other, gain, block diagram. Okay. So this is achieved by repeatedly integrating both sides of the differential equation to remove all derivative terms. Okay, so you want to continue to integrate and integrate and integrate till we are able to remove all the derivative terms. And the canonical form, therefore, is something like this, where we now have the y component on one side and the s component on the other side. The summation of k equal to 0 to n a sub k being the coefficient, integral y of t dt for values of k is the same as the summation given k 0 to n, b sub k being the coefficient, integral s of t dt for values of k. So you should note that this form is obtained after repeatedly integrating the differential equation. Now, the differential equation in this case means that y of t is a function of some input value s of t. So we now have separated them, right? Now, note that given this general form, after such integration, such that this integral, say s of t dt, given k, is the kth order integral. Okay. And now we can now design this. This is the canonical form. So we're now going to look at the canonical form. So let's wipe this so that I need more space. So we're now going to look at the canonical form given k equal to 0 to n a sub k integral y of t dt for k is the same as summation and 0 k equal to 0 to n b sub k integral s of t dt such that this integral s of t dt is the same as the kth order integral. So in the design, it means that we have s of t, this is the block diagram now, or the graphical approach, is fed into this adder. Fed into this adder. Then it comes into this block. Then it goes all the way into this block. Then it goes into another adder. Then we have a y of t. Yeah? So at this point, we have the integrator. Okay. So there's an arrow here, and there's an arrow here, right? Yeah. So this is a sub k. So we have 1 over a naught here, and then we have b naught, the coefficients, right? bk a sub k. Then here, we have these. So they are connected. So this comes into this. Then it goes into another integrator here. Goes into another integrator here. So this is, that's 1 over a naught. So this is a sub 1, b sub 1. Then this now goes into this. So this are added by this. This is added here, but these are subtracted, right? So this goes into another block. have this. Then we'll have this here again. And then this is added to. Then this comes here. Comes into this order. This is minus. So this is A sub 1. So this is A sub 2. Then this is B sub 2. So this goes into another integrator. So it goes on, right? Till we get into the final integrator here. And then voila. We have this. So this will be B sub n, and then this will be A sub n. So this also is positive. And this is negative, right? So you observe that all of these, let's change the color. All of these are coefficients of y. While all of these are coefficients of x. And then the coefficients for higher order derivatives. So let's say coefficients for higher order derivatives are that way. So we move down to coefficients here of lower order derivatives. Okay. So this is what we get. It's something like this. So how do we solve a problem? Okay. So let us look at one quick example. So let's assume we want to evaluate a system that has, okay, no, let's change the color. Let's make it look different on the screen. Okay. So let's assume we have 6y, that's the third order derivative, plus 2y second order, minus y plus 3y is the same as 4x second order derivative plus 2x minus x. So we have this. So you observe that this is similar to what we have here, right? So what do? We have 1, 2, 3 blocks here, plus this is the fourth block. So it means that we are going to have something like this, but I'll just wipe what is not relevant. So this is not supposed to be here. So this is not supposed to be here. So I'm going to have 3 integrators. So this is going to join this. And then this can be here because we do not have this at that level. Okay. So I have to wipe what's inside. I have to wipe all of these things that are inside. What just happened? Now, so we have this, which is 6, right? So from the canonical format is 1/6, and this comes in here. Now, this is the third order derivative. We don't have the third order derivative for X. So this is left open, right? So it goes in. So this second order derivative, and we have a positive 2. So we have 2 here. That's the coefficient, and it goes in. Then we have a -1 here. -1 is the coefficient here. We have -1. Then for this last block, we have 3. Okay? Then it goes on. Now, here, we do not have, so we are going to wipe this. I'm going to wipe this. Cross. Okay. Okay, so for this, at this level, is 4 because it's second order, so it's going to match with this, right? So that's at this level. So that's 4. Then at this level, that is 2, right? So that is 2, positive 2, right? Then at this level, it's 1, -1. So we have something like this, okay? Now, I want to quickly, okay, I have just a minute, so I'll just run through the state space, then we'll call it a day. Okay, so we don't have to take it over to the next class. So for the state space, we have state space equation.
Sorry, sir, I have a question, sir.
Okay, can I quickly run through this? Then we take the question, or go ahead. Let me hear you.
Sir, finish running through it, sir.
Okay, I'm very sorry, sir. Please, can you re-undo the diagram, the previous diagram, sir?
Okay. Okay.
Okay, sir. Yeah, the last input that you did for X, which is -1. So I actually
Yeah,
do not see
it should be -1. Yeah,
the...
it should be -1, right? Minus.
Yes, sir.
Yeah. Yeah, that's it. Okay. So we now come to state space equation. So this is another method for modeling continuous time systems, okay? So a state, so let's come to this, a state is any internal system variable whose next value depends on its current value, okay? So it contains information about how the system evolves in time, okay? That's what a state means. And for instance, we'll just consider an RLC circuit. So for an RLC circuit, we have the capacitor voltage for an RLC circuit, for instance, and then we have the inductor current as the state variables, okay? We call them state variables. Okay, so higher order differential equations that describe the system could be written as a series of first order differential equations relating the input, output, and the internal states. So we just draft one simple RLC circuit I picked somewhere. So plus minus. Not broken. So here we have the capacitor. Then here we have another resistor, right? So R1, L1, L2, R2, C. So let's say the current flowing in this direction is I1 of T, and the current flowing in this direction is I2 of t. So this plus minus V1 of t. Then here we have this terminals plus minus y of t, and the input is s of t. Okay, so for us to, now looking at this from what we just mentioned, what are the state variables? The state variables in this case, state variables. We said the inductor current and the capacitor voltage. So I1 of t, I2 of t, and V1 of t. Those are the state variables. So now we want to derive their relationship. So the next thing is to derive their relationship, okay? So if we write, I'll just do one, then run through. We are past time, right? So we are 3 minutes behind schedule. Then we'll look at examples much later. Now, let's write KVL, Kirchhoff's voltage law. Recall your fundamentals of electrical engineering. I also have some videos uploaded, so you can probably look up if you're beginning to forget some of these things. So if we write KVL around this, so that's minus this plus Li di dt, then we already have V1 here. So that will give us, once we manipulate the process, so that will give us L1, the I1 dt will be minus R1, I1 dt minus V1 t plus S of t, okay? So I'm sure you already, well, let's work this out. So it doesn't look like some magic. So here, the current is moving in this direction, right? So let's write KVL. So that will be this by KVL, right? That will be minus, right? Minus S of t. Recall your passive sign convention, right? Plus minus. So that will be I, that will be plus R1, I of t, then plus, then the current through this, the voltage will be plus L1, the I of t, dt, then plus V1 of t is equal to 0, right? So if we make this subject of formula, so that will be L1, the I, the 1, the I dt over dt will be the same as this will cross the equality sign minus R1 I of t. This will be minus V1 of t plus S of t. So that gives us this, right? So when you do same, you're going to get all others. So let's just run through L2, the I2 of t dt will be the same as minus R2 I of t minus V1 of t. This is by KVL, right? KVL. So if we do KCL at this point, you know, so we have C, the V1, the T will be the same. These two currents are flowing in, right? They're in the same direction flowing in. So that will be I1 of T plus I2 of T. So this is by KCL, right? At this node. So these two currents are flowing in. So, and that's the resultant effect. So once we have this, so the next thing now is that the series of state equations can be completely written in the matrix form. So I'll just wipe this because I still need these equations. So let's just wipe all of this. So if we now write this in the matrix form, the matrix form is usually referred to as the state space representation. So we want to put this now in the matrix form. And once we do that, we call that the state space representation, all right? So, so this is going to give us D dt, I1 of t, I2 of t, then V1 of t, right? Will be the same. So the coefficient. So we already made the subject of formula. So this would be negative R1 divided by L1, right? So this would be negative R1 over L1, then 0. Okay, for I2, no I2 component here. So the next now is V, right? That will be negative, it will be negative 1 over L1 because this divided by all of these, right? So for X, I'm going to have this. So it's equal to all the components, the input parameters, S of t. So for the S parameter is 1 over L1, right? Because 1 over L1 will be here. So that will be 1 over L1. So for the second also, so there is no I1 component here. So this is 0. Then this would be R2 divided by L2 negative. So negative R2 divided by L2. Then for V, so that will be negative 1 over L2. Negative 1 over L2. So here, there is no X component here, so that's 0. And for the last one, so I1, I2 have components here, but that will be 1 over C, 1 over C. So 1 over C, 1 over C. Now, V sub 1 does not have any component here, so it's 0. Then also the X component does not have any value, so it's 0. So we've written this. That's that. Then Y of t is also a function of 0 minus R2, 0 times I1 of t, I2 of t, V1 of t. Now, at the end of the day, we say these are three, we have 3 states here. And then we have 1 input and 1 output. So now if you look at this, let's assume we have this RLC circuit and we need to analyze it. Now that we have written it in the matrix form, we could do a whole lot of analysis, right? We could solve, we could get the stability and then the ease of analysis. Yeah, we could even use some CAD devices. We could use MATLAB. We could use some other tools to resolve this circuit. That's fine. So this is what it is. But, well, let me just put up the general notation, okay? So in a more general form, for the state space representation, so we have that X, first order derivative of X is AX plus BU, while Y, which is the output, the same as AX plus D. Now, all of these means that where X is the state, is the end state, okay, which is an n by 1 matrix. U is the M input, which is m by 1 matrix. Y is the K output, which is K by 1 matrix. Then A is a system matrix, which is n by n matrix. Then the B, C, they are coefficients. They are coefficients, which is n by m and K by n matrix. And then we have D, which is a constant, all right, which is K by 1 matrix. Well, this is where we'll stop. Probably, let's say in our next class, God willing, we'll try to solve some more practical problems. I think we can actually call it a day here today. Okay?
Thank you, sir. We love you,
Excuse me,
sir.
sir, please. How can we get the recorded video, please?
I'll try to upload it to my channel so you could access it from there.
Okay, all right. Thank you, sir.
Okay, do have a great day.
Bye-bye, sir.
Bye.
Thank you very much, sir.
We love you.
Happy holidays, sir.
Yes, sir.
Yeah, I think we should have.
Merry Christmas.
Yeah,
Bye-bye, sir. Bye-bye.
we should have our next class after Christmas.